Rich is gonna go ahead and we're gonna let y'all work on number 1. This is a totally different worksheet. This is a practice exam for gas laws specifically, okay? So we'll give you 4 minutes to work on 1 and 2. That's probably a little too, not enough time. So try to at least work on 1, and if you finish, go to number 2. There's 4 carbons right there. 2 on the double bond and then 2 over there. One, 2, 3, 4. Is this possible to do? Make straight these transfer. This one stays the same. 2 more minutes. Thirty seconds. Because you're the only students on the room. The only good students in the room. For sure. Yeah. You ready to impress all the ICSA future options? 10 seconds and time. Okay. So if you're on Zoom, if you're in class, tell me what the conversion from TOR to ATM is. Now. What's the conversion? All right, so 1 ATM is equal to 760 TOR. And what's another unit that this is also equal to? Equals 760 millimeters of mercury. All right, but we're only concerned with the TOR, right? So 1.6 times 10 to the 5th TOR, and our conversion is 760 TOR per 1 atmosphere. And when you did this, what number did y'all get? 2 point what?
Oh, 2.1, sorry.
2.1 times 10 to the 2nd. Sydney and everyone, looks like everyone got their money up. We got 2.1 times 10 to the 2. Corresponds to answer choice D. How many of y'all were able to finish 2 as well? Okay, good. You too. Okay. What about people on Zoom? Awesome. Sweet. All right. So a sample of helium gas occupies 2.65 liters at 1.2 atmospheres. What pressure would the sample of gas exert in a 1.5 liter container at the sustained temperature? All right, so it's clear that we are we increasing or decreasing volume? Okay, so we're going from 2.65 liters to 1.50 liters. So could we predict using our, I guess, some principles, should the pressure increase or decrease if we decrease the volume? What law are you using for that statement? So P1 V1 equals P2 V2. So
Boyle, just kidding, yeah, Boyle.
Boyle's law, right? And we're saying that we increase we're decreasing volume, so we're making the container smaller, right? So we would expect the pressure to, I see Sydney says the pressure should decrease. So Boyle's law tells us that pressure and volume are inversely related, right? So if volume decreases, then that means the pressure should increase, because that's what Boyle's law tells us, that pressure and volume are inversely related. Which is why if we didn't know how to go about this problem, but we knew the basic law, and in fact, this is the equation you would want to use to solve this problem. If you knew the idea that pressure and volume were inversely related, you should be able to at least eliminate some of the answers. So we know that pressure should increase. So right now our pressure was 1.20. When we put it in the new container, it should be greater than 1.2, right? So let's just cross out any answer choices that are not greater than 1.2. So 1.2 and D are crossed out. So you're left with a better chance at answering your question, right? So then we can just plug everything into our equation. So we have 2.65 liters in the beginning with 1.2 atmospheres is equal to 1.5 liters and some unknown pressure. When you solve for P, what do you get? 2.12, which is answer choice C. That was not too bad. We're gonna start easy and then work our way up. All right, so this is the basis of all gas laws and this entire chapter 5. Hopefully in a couple of weeks you're expert at these easy problems, and then we can go to the hard ones. So let's go and let you work on number 3. Give you 3 minutes for that, or yeah, let's do 3 minutes. So at 3:20, right now it's 3:17. No. You're up. We're trying to POW. Palmer was supposed to make benzoic acid with synthesis by benzene. What he did was methylchloride, Br2 and lime, sodium hydroxide, and then oxidized it all with carbon sulfates. What do you do? Ready? About 30 seconds. Fifteen seconds. And time.
All right, let's go. The sample of helium gas that occupies 12.4 liters at 23 degrees Celsius and 0.95 atmospheres. What volume would it occupy at 40 degrees Celsius and 0.95 atmospheres? What do you do?
One v one over two. B2, or B2. Don't ask me about those.
Let's see, combined gas,
Mhm.
CGL. But notice this number, right? It's 0.956. And what is this number?
No,
Well, just read it out.
atmospheres.
No, like, read it out.
Same. Oh, yeah, they're same.
So pressure is constant. So we don't even have to use the combined gas.
Okay.
And you notice that V and T are changing. So whose law is that again? V and T? Certain king in Europe. Yeah. Charles. Yeah, okay, Charles. How do you spell it? Charles? Law? I think that's it. Something like that. Okay, so V1 over T1 equals V2 over T2. So 12.4 liters of the volume over 23 degrees Celsius. Oh wait, it has to be in Kelvin, right? It does indeed have to be in Kelvin. So 23 plus 273. What is that again? What number would that be?
For what?
273 plus 23.
Like the answer or what?
Yeah.
Oh, it's 296.
296 Kelvin. So over 296, and then it's asking for the new volume, so we're solving for V2, and we'll occupy 40 degrees Celsius, so 273 plus 40, or if you want to be faster, you just add 17 to that, and that's your answer, 213. So solve for V2. V2 is going to equal 12.4 times 313 divided by 296. So when you solve it out, 12.4 times 13 divided by 296. You should get 13.11216 liters. And that corresponds to another. Does that make sense?
Technically, we didn't do it wrong, right?
No, you didn't, but there was a faster way to do it.
Yeah.
Because the way, if you use a combined gas law, the pressures will just cancel out. So, yeah, pretty much. And in the exam, every second counts. Anyway, any questions on that? Zoom people, room people? Children? All right. Let's see. A balloon has a volume of 1.2 liters at 24 degrees Celsius. The balloon is heated to 48 degrees Celsius. Calculate the new volume of the balloon.
It's the same law, right?
Is it the same one?
Yeah, because it's volume. Or you're looking for volume.
Exactly. It is Charles. So Charles law. That is not right. Charles's law, something like that. So V1 over T1 equals V2 over T2. What's our V1 again? Yeah, 1.20. What's our T1?
Oh, 24.0 plus 273,
Or was that equal to
397.
297? Equals V2 over, what's our T2? Just add 24 to 297,
321.
321. All right, so our V2, once again, is gonna be equal to 1.20 times 321 all over 297. So if we solve that out, that's 0, 1, divided by 297. And if we solve it out, we get 1.296 liters, which corresponds to answer choice C if you round. All right. Questions about that? Does that make sense? This is a conceptual. If the temperature of an ideal gas is raised from 100 degrees Celsius to 200 degrees Celsius, while the pressure remains constant, the volume will what? Shout it out.
Doesn't it decrease? Temperature increases.
All right, I'm gonna teach you a little trick. PV equals nRT, right? So here's the thing. If two things are on the same side of the equal sign, that means that they're inversely proportional. And we know this from Boyle's law, right? As pressure increases, volume decreases. Makes sense. And then here we have pressure and temperature. We know from Gay-Lussac's law that as pressure increases, the temperature also increases. So they're directly proportional. In this case, which two variables do we have in the PV is nRT equation? We do have temperature.
Well, you know, pressure is constant.
Yeah. And then we're being asked about the volume, right? So are they on the same side of the equal sign or opposite sides? So that means that they're what? Directly proportional. Directly. Meaning that when one goes up, so when volume goes up, temperature also goes up. So in this case, right? 100 degrees to 200 degrees, how do you get there? Multiply by what number? So the temperature, right, is doubled. So the temperature is doubled, what happens to volume? If they're directly proportional, they both increase by the same amount. Go up by how much? Yeah, it doubles. Directly proportional, all this means is two things increase by same amount. So since you doubled the temperature of this gas, you doubled the volume. That's why correct answer is B. Now, let's say that you went from 100 degrees Celsius to 50 degrees Celsius. What would happen then?
It would go down by half.
Yeah, go down by half. Basically, just look at your relationship between your temperatures and then determine your relationship on the volume based on that. Questions about any of that? Zoom people, we good? Sweet. All right. Number, so that was 4, 5.
At least give some of the others, because there are two.
All right, 9. Okay. An oxygen sample has a volume of 4.5 liters at 27 degrees Celsius and 800 torr. How many oxygen molecules does it take? We'll give you all 3 minutes. Solve this problem. We'll reconvene at 3:31.
Rich. You know, it's always from.
Set a timer for 3 minutes. Also,
That.
what was asked?
Oh. What's happening?
What's going on?
Just drag air resistance. What's happening underneath the truck? And how does that affect the drag? You're liquidating.
How is that? Right.
Plus friction.
Also, some weird physics.
Makes sense to me. Focus, I don't know, gratitude. You're gonna snack on it when you get hungry, because chocolate is actually edible. Holy stuff. Look at all the variables they give you. They give you pressure, temperature, and volume.
Yeah, we don't have an election.
They'll give you pressure, 800, 812. Whoa, whoa, this is a learning friendly zone.
She's not in love with today. That's based on.
Personnel affair.
Person.
Personally, my friends don't leave this, so.
Yeah, see? I needed a break, okay? You had a break on Tuesday.
It's supposed to be recorded.
Be muted.
Hey, have you been sending this to your mentee to get edited? A few more seconds. And time. All right. So an oxygen sample has a volume of 4.5 liters at 27 degrees Celsius and 800 torr. How many oxygen molecules does it contain? Good question. Now, what's the answer? Well, let's assign our variables. We're given volume, temperature, which we need to eventually convert that to Kelvin, because it's important that when we do gases, temperature is in Kelvin. And then pressure, which we should probably, depending on the equation we use, convert that to atmospheres. All right, so we're given volume, temperature, and pressure, and it's not given in a scenario of this is the before state, find the conditions in the final state, right? Because that's when we would use our P1 V1 equals P2 V2 when you have an initial state and then a final state, or your other laws like V over T equals V over T2. Clearly, that's not what we're doing. We're going to use the ideal gas law for this problem, because it's talking just about a single state, not before and after. So we should use PV equals nRT, and the variable that we should solve for, which would make sense, is the moles, right? Because if we find the moles of oxygen molecule, or if we find the moles of oxygen, then we can use Avogadro's number to find how many molecules of oxygen there are. So let's isolate N. So PV over RT is that. So now we also need to make sure our units are correct. So temperature should be in Kelvin, so 273 plus 27 should be 300 Kelvin. And 800 torr, we know 800 torr, and the conversion from torr to atmospheres is 760 atmospheres, or 760 torr is 1 atmosphere. And why are we converting to atmospheres? Why is it important? What? Okay, but pressure has many units. It can be in PSI, it can be. So you're onto the right track. But it's because in this equation, the ideal gas law, the R is in units of liters, atmospheres over moles times Kelvin. So you need your units to be in liters, atmospheres, and Kelvin for this equation 4. So that's why we're doing this. So when we do this, we get 1.0526 atmospheres. So now that we can plug everything into here, so N is equal to 1.0526 ATM times the volume, which is 4.5 liters, divided by 0.0821, which is our ideal gas constant. And then it is divided by temperature, which is 300 Kelvin. This equals, anyone get an answer for this part?
0.1.
0.19222. And this is the mole. Moles of O2 specifically. So let me just fact check that. I totally agree with you. 0.821 divided by 300. Interesting. 0.1923. It's all right. We'll go with this. Okay. So now what's the important number that we gotta remember to use? Avogadro's number. So should it be multiply or divide by Avogadro's number?
Multiply.
Right, so our units cancel out. So we know 1 mole of oxygen gas has 6.022 times 10 to the 23rd O2 molecules. And when you do that, third, you should get an answer of roughly 1.16 times 10 to the 23rd. And let's see, that corresponds to answer choice C. So does that make sense for everyone? If you were not able to solve it, I hope you see where you, I guess, got stuck in how to solve that in the future. Is there any tips or tricks I can give you? Make sure your units are the same. If it asks for how many oxygen atoms, what other step would you have to do? If it asks for oxygen atoms, how many oxygen atoms are in this sample of oxygen gas? What other step would you have to do? It's the same thing, but it's asking about oxygen atoms, not oxygen molecules. O2 versus O. Yeah, so after this step, if it asks for how many oxygen atoms, you would say in the next step, it would be 1 molecule of O2 has 2 atoms of oxygen. So then you would multiply it by 2. So you would multiply this number by 2 to figure out how many oxygen atoms. But that's not what this question is asking for. That was just a what if scenario, okay? All right, number 10. I'll give y'all 3 minutes to work on this one. Hey Siri, start a timer for 3 minutes.
3 minutes. Counting down.
All right, Rishi. Rishi.
Oh, that's just. That's. All the hydrolysis reaction, chaperones, just water and acid.
Yeah. All right, pretty much. You know how to do this one, Rich? Or you need some prep time? Oh, you're. You have a cyclic heavy acetone. What are we doing here? So you don't know what to do, or
No.
it says HGX. That's the more mass. It's 200 grams. Can't multiply by grams, so it's units of grams squared. Exactly.
That's what I do, but then if you divide, you just get one mole.
What's the more mass of mercury? Looks like you get one more. Is it completely one mole? Or is it like 0.99? Please don't know. You don't.
I didn't.
You'll do this. All right, Rich, time's up. POW time is up. Time to be a TA, projected one.
All right, mercury vapor contains mercury atoms. We thought, what is the volume of 200 grams of mercury vapor at 822 Kelvin and 0.5 atmospheres? So what's our first?
Converting grams of mercury to moles.
Yeah, that's a pretty good first step. 200 grams of mercury. And then if we look at our periodic table, right about here, you will see that there is approximately 201 grams in one mole.
That's showing up my entire schedule.
201 grams. One mole. So that's there. So then we'll convert to our moles. This should be approximately like 1. So 200 over 201. Solve that out. We'll get 0.995 moles. Mercury. Mercury. What's our next step?
Plugging it on perfect.
PV. So PV equals nRT. So our volume is nRT divided by P. So our N, right, we got from the step here, so 0.995 times R is 0.0821. And then temperature, which is 822 Kelvin, as stated in the problem. And then our P all over 0.5 atmosphere. So if we solve it out, we just do times 0.0821 times 822. equals that divided by 0.5. And we will get an answer of 134.3 liters. And I know this doesn't round up, but since I rounded up to molar mass, it's probably close to 130. Does that make sense?
All righty. Good job.
All right, number 6. A 437 gram sample of a certain diatomic gas occupies a volume of 3 liters, 1 atmosphere, and a temperature of 45 degrees Celsius. Identify the states.
Give y'all 3 minutes. It's a nice question. Yep. Expect to see something like this on your test.
That's outside. And I don't have paper today, so.
Not so fast. Get it control.
All we need to turn to my phone. Do we have a-
Hey, they have our shoes random. That laptop needs a lot of work.
Sorry, you guys.
I have to charge my iPad 5 times a day for how much I use it. Studying. So possible. I'm pretty sure all of these need to be done mile faster. Or else it's not gonna work.
Well, all of them. They're just ones that form.
The ones that form images and images. You know the mechanisms for that?
Yeah, I should.
I think it should. This, do you?
Yeah.
2 minutes. Intermediate species. Or should have. No. 20 seconds. It's managed. That plus. You don't see it plus over the top. This is not got it. And time. Who was able to finish? Oh, I wasn't. You can't do a proton transfer here, because if you do, you never become your intermediate, which is a carbonyl elite. You'll never end up with something that has.
Why not here? You do here. Last one.
All right, let's see.
All right. 4.37 gram sample of certain diatomic gas occupies a volume of 3 liters and at 1 atmosphere, temperature 45 degrees Celsius, identify the gas. So what equation do we use? Little this guy. PV equals nRT. So what are we trying to solve? Why?
You can find the gas by the minutes.
Yeah, so N equals PV over RT. So 1 atmosphere, volume 3 liters. R is 0.0821. And then what is our temperature gonna be? Sounds right. It is right, 318. So we do that as equal to, let's see, 0.081 times 18 gives me. All right, so if you do that, you will get 0.115 moles. And then from here, you can find molar mass. So molar mass, again, is in grams per mole. So if you have 4.37 grams, you just divide by moles, 115, so grams of moles. So 4.37 over 0.5. And you get an answer of 38 grams per mole. Wait, but none of these gases have a molar mass of 38 grams per mole. So you do 38 divided by 2, and you get 19 grams per mole.
Which corresponds to what? 19 grams per mole. What atom? Here our table. Fluorine.
Exactly.
There is another way you could do this that I thought. Personally, I would have done it this way. I'll do it in red so you can decide which way you would like more. Is using that good old density equation. We're not really dealing with density, but it's nice because we know this is our equation. And remember, P is equal to P times the molar mass over RT. And look at the variable that we can directly solve for, molar mass. So you can solve for it directly and you get your answer. You don't have to do it. Whereas in this case, you solve for N and then you use this other equation, plug the N value in here, then you get your answer. If you do it this way, you get mass times RT over PV is equal to molar mass. Plugging all these variables in, we get our sample of 4.37 grams multiplied by 0.0821 multiplied by our temperature of 45 degrees Celsius, which is 318 Kelvin. Our pressure was 1 atmosphere and our volume was 3 liters. So 1 ATM and then 3 liters. If you plug all this in, you get a nice number of 38 grams per mole. And then you divide it by 2, which is 19. And boom, that's how personally I would have done it. You, whatever way suits you is the way, whatever way makes sense to you is the way I would, do it on the exam. But personally, I would have taken the quicker route, which is, I think, the second way. Because on the exams, we want to, save time. So that way we have a lot of extra time for reviewing and looking at the other questions that may be more difficult. So again, you choose which way you like more. But yeah, there's multiple ways to solve all these problems. All right. With that, it's 3:55, so we'll let y'all go early. Just because the rest of these problems are a little bit more interesting. Okay, maybe if you care, you can take a picture of them. And you can go over them on your free time, and we'll do them on Friday tomorrow. So maybe you can do this if you're bored tonight and you don't want to watch Netflix, you want to study chemistry instead, because chemistry is more fun than Netflix.
Or you
right?
can do chemistry while watching it.
Or you can do chemistry while watching Breaking Bad, which is a show about chemistry. So whichever one works for you. Again, we thank all of y'all. Like and subscribe and hit the bell icon. And yeah.
Hey, yo, Mr. White, that wraps it up, yo. All right, I'm gonna head out.
See ya. Thank you, Sydney and Taylor and the other person that was in the Zoom, which I cannot see because it was